In this lecture, we'll be discussing periodic trends of three different properties of elements. We'll be discussing the atomic radius, ionization energy, and metallic character. And we're going to be able to compare and contrast different elements within the same period or the same group and be able to tell how their atomic radius or ionization energy or metallic character compare to each other based on their electron configurations and the number of protons they have. A periodic trend is a trend or pattern. A trend just means a pattern. And this is a pattern that is repeated in each row on the periodic table. So we see the trend repeating periodically, which is why it's called a periodic trend. The first trend we're going to study is atomic radius, which basically means the size of an atom. For our purposes, we're going to use the term radius just like you would in algebra or in geometry, where you look at radius as being half the diameter of a circle. In reality, atomic radius actually has more to do with the distance between two atoms, but we're just going to use this in general to mean the size of an atom. The second trend we're going to look at is called ionization energy. It's the amount of energy that is required to remove one of an atom's valence electrons if another atom was trying to steal it. So we have a picture here of a thief, and a thief is a good example because this thief is trying to remove a valence electron from this atom over here. And ionization energy is a characteristic of this atom, how tightly it holds on to its valence electrons. So it is a characteristic that describes how much energy it's going to take a different atom to remove one of its electrons. The third property we're going to study is metallic character, and that has to do with whether an element is a metal, a nonmetal, or a metalloid, which means sort of a combination of a metal or a nonmetal. Some terms you need to know in order to understand these three properties are nuclear charge and electron shielding. First of all, nuclear charge is the positive charge of an atom's nucleus. This positive charge attracts the atom's own electrons. It can also be strong enough to attract electrons from another atom. We can quantify this, actually calculate the charge by subtracting the number of core electrons from the number of protons in the atom. And the trend is that the nuclear charge gets stronger as the number of protons increases. And this makes sense because the number of protons is what determines the nuclear charge. Protons are positive, and hence the nuclear charge is a positive charge that is the sum of the protons. For example, in an atom of magnesium there are 12 protons and 12 electrons. Those electrons are divided into 2 of them being valence electrons and the remaining 10 being core electrons. So if we were to calculate the nuclear charge of magnesium, it would be 12 minus 10, which leaves us a positive 2 charge. So the effect that the valence electrons are feeling, they are feeling a positive 2 charge being pulled from the nucleus. This magnetic charge, it's not exactly magnetic, but we can represent it as being a magnet, and this nuclear charge is going to be pulling the valence electrons in and this influences the size of the atom, the radius, and it also influences how much energy it takes to remove these electrons. And if this charge is very strong, it can even be attracting electrons from other neighboring atoms. The second term we need to know is electron shielding. Electron shielding is the protection of the valence electrons from the nuclear charge by a shield of core electrons. So inner electrons or core electrons are going to absorb the nuclear charge, and that's going to make it so that the valence electrons do not feel that outer charge or that nuclear charge as much as the inner electrons. The electron shielding gets stronger as the number of energy level increases, which makes sense because that means there's more core electrons to be shielding. So if we look back at magnesium, here we have our 12 protons being represented as a magnet pulling on these valence electrons. However, all of these inner core electrons are shielding or protecting the valence electrons from that charge. So when we look at the nuclear charge and we say that it's positive 2, the reason it's not positive 12 is because we have to take into account the electron shielding by the inner core electrons. Let's look at our first trend. Atomic radius. Atomic radius, as you go down any given group in the periodic table, the atomic radii of the elements in that group are going to increase or get larger. The reason this is that all atoms in the same group have the same nuclear charge, Meaning, if you were to take the number of protons they have and subtract the number of core electrons, you would end up with the same nuclear charge, or the same ratio of proton to core electrons. So their nuclear charge is the same. However, elements with more energy levels are going to have more electron shielding. And the greater the amount of electron shielding means the valence electrons are being protected from being pulled inward, and this allows the radius to be larger. So if we look at magnesium, we see again we have magnesium has the 3 energy levels, 1, 2, 3, and there are 2 energy levels of core electrons protecting this outer shell. If we compare this to calcium, the next element down in the group that magnesium and calcium are in, the alkali metals, calcium has 1, 2, 3, 4 energy levels. Therefore, calcium has 2 or 3, a total of 3 levels of electron shielding that are preventing these valence electrons from being pulled in. So calcium is going to have a larger atomic radius. If you compare magnesium and calcium, you can see that magnesium has fewer energy levels, so it has less electron shielding, therefore a smaller atomic radius. Calcium, on the other hand, has more energy levels. It has more electron shielding, and therefore the larger atomic radius. And we could predict this by knowing the trends. We could also look at the electron configuration for each of these elements and be able to determine this answer. Secondly, we need to know the trend going across from left to right. The trend for atomic radius is that the atomic radii of the elements are going to decrease across a period. The reason being is that all elements in the same period have the same electron shielding because they have the same number of energy levels. Therefore, the elements with more protons are going to have a stronger nuclear charge, and compared to having the same electron shielding, a greater or stronger nuclear charge pulls the valence electrons harder. This causes the radius to be smaller. So again, if we look at magnesium, and it has only its 3 levels, and only 2 of these are electron shielding. If we compare this to something else in the row, chlorine, chlorine also only has 3 energy levels. Therefore, it also has the exact same amount of electron shielding. However, if we look at the protons or the nuclear charge in chlorine is much stronger because it has more protons. And if you have the same amount of defense or the same amount of electron shielding versus a greater charge pulling the electrons in, they're going to be pulled more strongly, and they're literally going to shrink the radius of the chlorine. So if we compare the two, magnesium has fewer protons and a lower nuclear charge, and therefore a larger atomic radius. In the same row, with the same amount of electron shielding, chlorine has more protons, and therefore a higher nuclear charge, which is pulling those electrons in more strongly to create a smaller atomic radius. The second trend that we need to know about is ionization energy. When we look at any given group going down, the ionization energy of the elements decreases down a group. All elements in the same group have the same nuclear charge as we discussed previously with atomic radius. Elements with greater electron shielding, however, are going to protect their valence electrons more from the nucleus, and therefore it requires less energy to remove a valence electron that is being shielded, which means the ionization energy is lower. So magnesium, as we've already stated in a few examples, is going to have 2 energy levels worth of electron shielding, so its valence electrons are fairly easy for this other atom to steal. We'll have this thief be representing another atom. However, if we compare this to calcium, calcium has even more energy levels that are shielding these outer electrons, so they are held on even more loosely, and you can see this thief is very happy because he needs to use a very small amount of energy. So again, with the magnesium, he needs to use some of his strength. This thief needs to use very little strength, meaning it has low energy that needs to be used to remove the outer shell electrons. So in comparison, magnesium has less electron shielding, and we know this because it has less energy levels. Therefore, it's going to have a higher ionization energy because the outer shell electrons are not protected from the nucleus. as much as something with more electron shielding. And higher ionization means it is going to be harder for another atom to remove those electrons. Calcium, in comparison, has more electron shielding because it has more energy levels. It therefore has a lower ionization energy because the electrons, the outer electrons, are more protected from the nucleus, and so they're not being held onto as tightly, and they are therefore easier to remove. We also need to know the trend for ionization energy going across the periodic table. For any given period across, the ionization energy of the elements increases across a period. The reason is because all elements, as we know from discussing atomic radius, have the same electron shielding because they have the same number of energy levels. But the elements with more protons have a stronger nuclear charge, and a stronger nuclear charge means they pull their valence electrons harder. If these electrons are being pulled on more hardly or harder on by the nucleus, it's going to require more energy for a thief to remove a valence electron, which means the ionization energy is greater. So magnesium only has 3 energy levels, so it only has 2 layers of core electrons that are shielding it, but its nuclear charge is 12. We can compare this again to chlorine, who has a much higher nuclear charge, but the same amount of electron shielding. Therefore, these electrons are going to be pulled on more tightly, which is why the radius of chlorine is smaller, but that also means it requires more energy for this thief who is now angry. It requires more energy to remove one of chlorine's valence electrons because they are being held on very tightly by the stronger nucleus that has a stronger nuclear charge. So when we compare these two atoms, magnesium has the lower nuclear charge with less protons. It therefore has a lower ionization energy, and it makes it easier to remove its electrons. Chlorine has the higher nuclear charge because it has more protons. It therefore has a higher ionization energy because the electrons are being held onto more tightly, and they are harder for another. The third trend we need to know about is metallic character. Metallic character has to do with whether an atom is a metal, a nonmetal, or a metalloid. The trend going across is that the metallic character of the elements will decrease across a period. The reason why is that metallic elements, ones that are classified as metals, typically have 4 or less valence electrons, so they will choose to give away electrons to other atoms. However, nonmetal elements are the opposite. They have 4 or more valence electrons and will usually take electrons from another atom. The metalloids, or semimetals, they all have around 4 valence electrons, 3 or 4 or 5, and so they do not follow these rules exactly. So for example, if we compare magnesium and chlorine, magnesium is on the left side of the periodic table. It has 2 valence electrons. Anything with 4 or fewer tends to give them away, which classifies magnesium as a metal, and we recognize this as being metal because it's shiny and grayish in color. As opposed to chlorine, chlorine is in the halogen column on the right side of the periodic table with 7 valence electrons. The rule is that atoms with 4 or more generally are going to take electrons from another atom, which classify this as a nonmetal, and we can see this as being a nonmetal pretty classically because it's a yellowish gas, and here we see the electrons around the outside. The trend is different for when you are talking about up and down in any given column. The metallic character of the elements in a group usually stay the same in a group. And again, this is because metals and nonmetals are classified by how many valence electrons they give away or they take, and all elements in the same group have the same number of valence electrons, so they are all going to behave in the same way. Again, for example, if we look at magnesium and calcium, we can see these are both classically metals with shiny silverish in color, and it's because they both have 2 valence electrons, so they behave in the same way by giving them away, which makes them metals. In our next lecture, we're going to be talking a little more about metals and nonmetals and their characteristics.